Okay, the topic today is going to be an introduction to molecular symmetry. And in particular, we're going to be looking at molecular symmetry in the framework of point group theory. Okay, and in point group theory, we are going to treat the molecules as being semi-rigid. And we're going to use what are called symmetry operations, right? And these include reflections, rotations, inversions, and so forth. In order to describe the symmetry of molecules, symmetry of a molecule, and its rotational, vibrational, and electronic states. Okay, and yeah, so when I say semi-rigid, what I mean is that the nuclei do not vibrate very far from their equilibrium position. So the molecule basically maintains the same shape. So if you have a non-rigid molecule that's undergoing large amplitude motion, or it's isomerizing or something like that, you might need to apply a different type of theory to look at its symmetry properties. So for non-rigid molecules, you can apply a theory that's called complete nuclear permutation inversion. Group theory. And this theory is based on exchanging equivalent nuclei. And the reason why this is convenient for non-rigid molecules is because no matter what the geometry of the molecule, you can always take two equivalent nuclei and exchange the labels and look at how that affects the wave functions and so forth of the molecule. Okay, but this complete nuclear permutation inversion group theory, CNPI theory, that's going to be beyond the scope of this course. And in this course, we're going to focus on point group theory. Okay, so yeah, I've already mentioned these operations, right? These symmetry operations. So let's give a formal definition. What is a symmetry operation? So a symmetry operation this is a geometrical action that leaves the nuclei of a molecule in indistinguishable positions. Or in other words, it leaves the molecule in an equivalent configuration. Okay? And so just to give you an example of that, we could consider a water molecule. And you know, I could label the hydrogen atoms hydrogen 1, hydrogen 2. And if we consider the symmetry operation where we reflect the coordinates of each nuclei through a plane that bisects the right, this you know, these OH bonds, right? So a plane coming out of the page going through the oxygen atom like this. Right, this is an operation called sigma V. This would basically reflect the positions of the nuclei so that H2 would, or the hydrogen labeled 2 would be over here on the left-hand side, the hydrogen labeled 1 would be over here on the right-hand side. But we can only tell the difference between this geometry and this geometry because I put these labels on the hydrogen atoms. And in reality, hydrogen atoms don't come with numerical labels attached to them, right? And so this configuration would be equivalent to this configuration. If I didn't show you these labels, you would not be able to tell the difference, right? And so any symmetry operation that leaves the molecule in an equivalent position, or the nuclei of the molecule in equivalent positions, that's called a symmetry operator of the molecule. Okay? All right, so before we get into symmetry operators, we're going to talk a little bit about operator algebra. Which is something that you're probably already at least a little bit familiar with because we use a lot of operator algebra in quantum mechanics. But basically an operator that operates on a function, you can think of it as, okay, if you have an operator, if it acts on a function, f, and f could be a function of, you know, the coordinates x, y, z, or, you know, it could have more than 3 coordinates, independent coordinates. Basically, the operator transforms that function into some other function, g of x, y, z, etc. Okay? And so an example using a symmetry operator. So if we have this sigma v operator that we discussed up here, right? Let's say that, I'll give you a coordinate system. So let's say the coordinate system is oriented like this, right? So the x-axis is coming out of the plane of the board, out at us. Then this sigma v operator, this would be a reflection across the xz plane. And basically, if you reflect the coordinates of any function across the xz plane, you're going to map the y-coordinate into its negative, right? But you leave the x and z coordinates unchanged. And so the sigma v operator, right, this reflection operator operating on some arbitrary function f of x, y, and z is going to have the effect that it's going to map this function onto the same function, but now it's going to be the function of x minus y, comma, z. Okay? And you can also operate multiple operators consecutively on a function. So if I take some operator x and some operator y and operate them consecutively on the function f, then the way that we understand that is that basically first we operate y on f, and then we take the result and we operate the x operator on the function that we get after operating y. So basically the operators operate from right to left, right? The rightmost operator operates first, followed by the next one. Okay? All right, and in general, operators do not commute So in general, if you have an operator x times y, that is not equivalent to having y times x. Okay, so some operators do commute, but a lot of them do not. So in general, xy is not equal to yx. Okay, but they are associative and distributive. Okay, and so what does that mean? Well, the associative property means if you have A times B times C, then if you group B and C together and operate A on them, then that's equivalent to if you have the A times B, the operator that you get by operating A on B times the C operator. Okay, so this is the associative property. And the distributive property says that if you have A operating on B plus C, then that's equivalent to having A operating on B plus A operating on C. Okay? And whenever you manipulate operators in this way, you should keep in mind that it's always sort of assumed that eventually these operators are going to be operating on some function, even though we might not explicitly write the function here when we're doing the operator manipulation. Okay? All right, so I've already mentioned a little bit about the symmetry operators. So what are the symmetry operators that we're going to apply to molecules? Okay, so the first symmetry operator, which seems really stupid, but actually it's for mathematical reasons very important, is what's called the E operator. This is an identity operator, which basically does nothing to the molecule. The reason why it's called E is because these operators were first developed by German researchers, and E stands for the German word Einheit, which means unity. So it's a unity operator or an identity operator. Okay, the next type of operator is a rotation operator, and these are called in point group theory C sub n operators. And a Cn operator rotates the molecule or the coordinate system, or actually the molecule or the function, clockwise by 2 pi over n radians. So, basically if you have a Cn operator, then you'd have to apply that operator n number of times in order to rotate 2 pi all the way around the circle. So for example, a C2 operator, that would rotate the molecule by 180 degrees, right? Or a C3 operator, that would rotate you 1/3 of the way around the circle, so that would correspond to a rotation of 2 pi over 3 or 120 degrees. Okay, and the axis, the rotational axis with the largest value of n is called the principal axis of the molecule. Okay, there's a couple other important types of symmetry operators that we need to consider. The sigma operator, This comes from the German word. So sigma is for S, and S is for Spiegel, which means mirror in German. This involves reflection through a plane. Okay? And there are various types of reflections that you can have. If the reflection is in a plane that also contains the principal axis, then it can be either a sigma V or a sigma D. Right? So sigma V is through a plane containing the principal axis. But if that plane happens to bisect two C2 axes, then sometimes instead of sigma V, it's called sigma D. And I wouldn't worry too much about the distinction between sigma V and sigma D, but sometimes it's useful to classify one set of reflection planes versus another set of reflection planes. Right, and we just do that with the labels V and D. Okay, but then there's a completely different type of reflection, which is called sigma H. H is for horizontal, V is for vertical. And the sigma H is a reflection across a plane that is perpendicular to the principal axis. Okay? So, just to look at some quick examples of these things, let's say you had a BF3 molecule. This is has a planar geometry, so it's trigonal planar. Then this would have the principal axis would be the axis that's coming out of the page of the board, and this would be a C3 axis, right? Because it takes 3 rotations to go all the way around the circle, right? So rotation by 120 degrees would leave, of course, the fluorines in equivalent positions. So if I apply a C3 operation on this molecule, then it's going to rotate 120 degrees clockwise, and F1 is going to end up here, F2 is going to rotate over here, and F3 is going to rotate over here. Okay? And the same molecule also has some reflection symmetries. So for example, there is a sigma V reflection. Right, that basically reflects the molecule through the plane coming out of the board, right, in the position of the dotted line, like I drew it here, along the BF1 bond. This would be an example of a sigma V, because this plane contains the principal C3 axis. And if we operate sigma V on this molecule, then basically the position of fluorine number 1 is going to be unchanged, but you would interchange F2 and fluorine 3. But overall, the molecule is going to end up in an equivalent configuration. Okay? All right, there's a couple more symmetry operations to consider. So the next one is an improper rotation, and that one is called N. This is an improper rotation. And in an improper rotation, you can understand this as two consecutive symmetry operations. First, you rotate, you do a CN rotation, and next, afterwards, you reflect about an axis perpendicular to the CN rotation. So that would be a sigma h. So perpendicular to CN. Okay, and just to give you an example of that, if you have a ethane molecule in its equilibrium configuration, then that would look something like this. So you have two carbons. Let's say you have H1, H2 is coming out of the plane of the board, H3 is going into the board, and then over here you have let's see, H4, let's say H5 is going into the plane of the board, and H6 is coming out of the plane of the board. I'm sorry, the H5 and H6. Okay? So, if you apply a, first apply a C3 operation, then so we're going to apply the C3 operation along the carbon-carbon bond, and that's going to rotate each of these methyl groups by 120 degrees. Oh, I'm sorry, yeah, this should, I'm sorry, this should be a C6. I said that wrong. Okay, so we're actually going to rotate 60 degrees, right? So if we do a C6 rotation, then basically hydrogen 1 is going to rotate, or let's say hydrogen 3 is going to rotate, you know, upward but still behind the plane of the board. Right, H1 is going to rotate so that it's coming out towards us. And H2 is now going to be in the plane of the board. And on the other side of this molecule, if we do a C6 rotation, let's see, H5 is going to end up in the plane of the board. H6 is going to be still coming out at us, but now it's going to be pointing down. And then H4 is going to be going into the plane of the board. Okay? So there's a C6 rotation, and then in order to do the S6 operation, we're going to next do a reflection through the plane that contained this, or that's, I'm sorry, that's perpendicular to this rotation axis, right? So we're going to reflect through this plane right here. So if I do that, then I'm going to get, I guess I can also label the carbons 1 and 2. Right, so that reflection is going to put carbon 2 on the left-hand side, carbon 1 on the right-hand side, and then H6 is going to get reflected over here. It's going to be coming out of the page. H4 is going to be going into the page. H5 is going to be in the plane of the board. And let's see, H2 is going to be in the plane of the board down here. H1 is going to be coming out of the plane of the board, and H3 is going to be going into the plane of the board. Okay? So now, if you compare where we started and where we ended up after the SN operation, so going from here to here, this would be an S6 operation. You can see that we've reversed the, we've exchanged the two carbon atoms, and we've exchanged a whole bunch of the hydrogen atoms, but the overall geometry here is the same as the geometry here. So we would say that ethane in the staggered configuration has an S6 symmetry. Okay? There's just one more symmetry that we need to consider. It's actually a special case of the improper rotation. And that is inversion symmetry. Technically, an inversion is the same as an S2 operation, but it's a special type of operation, and usually it's given a special name. So we call this one I for inversion. And this inverts all atoms, or all nuclei, through a point, right, basically through the center of mass of the molecule. Okay? And so, an example of that would be, if you have an ethylene molecule and if you apply the inversion operator, basically each, the coordinate of each atom is going to get mapped onto, if the coordinate now is XYZ, it's going to get mapped onto minus X minus Y minus Z. So we're going to flip the molecule inside out through the center. And so if we do that, we're going to end up with C2 on the left-hand side. C1 is going to be on the right-hand side, right? We flip those. H3 is going to end up down here. H4 is going to end up here. H2 is going to end up on the upper right-hand side, and H1 is going to be inverted down to the lower right-hand side. Okay? So, yeah, like I mentioned before, just a little bit more about operator algebra. Right, so symmetry operators, like other operators, do not, in general, commute with each other. And so as an example, if I take this famous group theory book by Cotton, if I apply a C4 rotation about the y-axis, followed by a C4 rotation about the x-axis, then I end up in a different configuration than if I first rotated C4 about the x-axis and then rotated C4 about the y-axis, right? Now the book's in a different configuration, right? So, in this example, C4 about the x-axis times C4 about the y-axis is not equal to C4 y times C4 x. Okay. Operators always have an inverse. And an inverse just undoes the operation that the operator does. So for example, the inverse of the C3 operator, so inverse operators, let me grab another pen because this one's seeming a little bit low on ink. Okay, so the inverse of the C3 operator, you can think of it two ways. If you rotate clockwise by 120 degrees, you could either rotate counterclockwise by 120 degrees, or you could rotate clockwise by 2 times 120 degrees, right? Because then if you rotate once 120 degrees, and then another 2 times 120 degrees, then you've rotated 360 degrees, which is the same as doing nothing. So the inverse of the C3 operator is the same as the C3 operator squared, which you could also write as the C3 halves operator, right? So this would rotate pi over 2, or I'm sorry, 2 pi over 3 halves, right? Or in other words, it's going to rotate 2 times 2 pi over 3, right? So 2 times 120 degrees. Okay. Okay, and if you have a series of operators that is applied consecutively, you have A, B, C, then the inverse of that overall operator that you would get by consecutively applying A, B, and C, that, it turns out, is equal to the inverse of C times the inverse of B times the inverse of A. So the order of these 3 operators when you take the inverse ends up getting reversed. This is kind of analogous to what you're probably familiar with matrix algebra, right? The inverse of a matrix times a matrix is the, second matrix inverse times the first matrix inverse.